Okay, Uri, go ahead.
Okay, thank you very much. Thank you for inviting me. Can everyone see the screen, right? It's, I can start. So I want to loosen the atmosphere a little bit with a funny cartoon of humans decided to demote Pluto. They decided that Pluto is no longer a planet, it is a dwarf planet. And so I think this is quite funny. Pluto is a little bit insulted by this decision. But I think what's really funny about this cartoon is that it's a good setup for the next cartoon, which is even funnier. Pluto is getting his revenge at the end. So in a few billion years, the sun is going to become a giant. It's going to expand. It's going to swallow all of the inner planets in the solar system. And of course, it's going to affect the other planets. The closer they are to this giant star, the more they will be affected by this changing in the star and the evolution of the star. And of course, Pluto being 40 astronomical units away is having his last laugh at his bigger brothers. So I find this a little bit amusing. Now enough with the funny cartoons. Let's talk schematics. So this is a schematic of the solar system. What we see here is the inner part of the solar system, what we call the terrestrial planets or the rocky planets, and the asteroid belt and the orbits of Jupiter and Saturn further out. Now in the middle, we have, of course, the sun. This is what we call a main sequence star, a star that fuses hydrogen in its core. And after, say, 11 billion years, the star becomes a giant. So we call this, technically, we call this an RGB star, a red giant branch star. And then it becomes an AGB star, an asymptotic giant branch star. And I'm not going to focus exactly on what's going on inside the star. Enough to say that during the AGB phase in particular, the envelope of the star is blown away by radiation pressure. And then what we have in the end is the remnant of the star, the core of the star, the degenerate core of the star, which we call a white dwarf. Initially, it's very hot, and this is why it's very white, and we call it a white dwarf. So what we have here in the end is a white dwarf. The inner solar system basically is gone. Mars probably gets to survive, and the asteroid belts and Jupiter and so on. And you also see that the orbits have expanded. This is because, as I said, the star loses mass. So by conservation of angular momentum, all of the orbits have to expand as well. And then what happens is the same that happens in our solar system. A bunch of planetesimals, they can be asteroids or comets or planets or moons. They're being perturbed into what we call tidal crossing orbits. So this is actually only a partial list of all the various studies that tell you what sort of mechanism can cause these planetesimals to become perturbed. And they assume a very eccentric orbit. They come from at least several AU, of course, because the giant star expands to almost the distance of Mars. So they come at least from a distance of several AU, and they come very close to the star. Their pericenter, the closest point to the star, to the white dwarf, if it is interior to what we call the tidal sphere or the Roche limit, this is the region or the zone close to the white dwarf in which the tidal forces are more important than the gravity of this planetesimal, and it's just being ripped apart, okay? So what will happen, and I'm really hand waving this, I'm not telling you the whole story just right now. This forms a kind of a disk of debris. And from this disk, we have accretion onto the white dwarf. And some of this material will actually be observed on the white dwarf, as we will talk about in a minute. Of course, we will not be around to observe any of this. This will happen in approximately 5-6 billion years into the future. But what we can say, yes.
I have a question about it. So you mentioned that you have these planetesimals that have a very eccentric orbit.
Yes.
Where are they now? Why don't we see them now? This is my first question. And my second question is related to that. How many of them are there? So how long it's going to take to form this disk?
Okay. So regarding to how long it takes to form this disk, I will address this question later when I show you really state-of-the-art numerical simulations of how you form disks. Regarding where are they now, they're destroyed, of course. I mean, in other, not in our solar system, of course, in other solar systems, they become destroyed. They create an eccentric disk, which then evolves and eventually they form some kind of an accretion disk. So we don't see them, we see the accretion disks, but
right
actually.
Now, you mentioned that these planetesimals will show up after the sun will go through a red giant phase, right? And then collapse into a white dwarf. But where are these objects that would eventually, they need to have high eccentricity. So they need to be there somewhere, or they need to be, somehow change their eccentricity. So where are these objects right now?
Oh, these objects can come from any number. As I said, there are any number of mechanisms that can perturb the objects and inject them into the inner solar system. There are some papers about objects that are perturbed by, let's say, the gravitational interactions in a system where you have a giant planet and an asteroid belt. There are some papers about 2 or more giant planets that interact with each other, and sometimes they perturb planetesimals into these objects. If you want to believe that this will happen, just look at the solar system. Every now and again, we have comets that are perturbed into even sun-skirting objects. Sometimes they come so close to the sun that they actually skirt the sun or come within 2 or 3 radii of our sun. So, I mean, you see this all the time. This is caused currently by maybe stellar flybys in the outer solar system, in the Oort cloud. Sometimes they're perturbed by a giant planet. If a comet passes close to a planet, say close to Jupiter, Jupiter can give it a kick and it will go into this kind of really eccentric orbit close to the sun. So similar things, similar ideas have been proposed for post main sequence systems, for white dwarf systems. A lot of different mechanisms that can actually inject these planetesimals into this kind of orbit. Okay, so it's not one mechanism, it's many mechanisms.
Okay, but maybe I'll refer to that. Why don't we have now an accretion disk around the sun then?
Well, of course it's different. The sun is not a white dwarf. The accretion disk, and I will get to this in the coming talk, the accretion disk is in what we call the Roche limit, of course. And the Roche limit is proportional to the radius of the star times the ratio between the densities to the power of 1/3. So if you talk about a white dwarf has a density of 1,000,000 times more than a regular star. So of course it has a very extended Roche limit in comparison with the size of the white dwarf. So you expect these disks to form in very compact stars, but not necessarily in sun-like stars, because the Roche limit of the sun is approximately the size of the sun, right? So you don't expect this to happen. And also you need the density of something to be lower than the density of the sun. Not a lot of objects have lower density than the sun, maybe comets and things like that. But planets, of course, they have higher density than the sun. So if they go near the sun, they will not break up, okay? So, it depends on what kind of central mass you have. If it's a white dwarf, you can form these disks. But don't worry, I will talk about this later on.
Okay, thank you.
Okay. So my talk basically has 3 parts or 3 sections. In the first section, I'm going to talk about the white dwarfs themselves and their atmospheres and the stuff that pollutes the atmospheres, the planetary material that pollutes the atmospheres. In the second part of the talk, I will talk about the environment of the white dwarfs, so the debris around it, what sort of debris we have and how we can explain how they form, how they evolve, and so on. And in the last part of the talk, I will briefly go through several objects that are seen currently orbiting white dwarfs, either disintegrating around white dwarf or intact. Their effects are being monitored either directly or indirectly. So I will show some of these publications. They are very high impact publications that are well known throughout the astrophysical community, not just the white dwarf community. So let me start by talking about the metal pollutants. So again, as I already touched on, we have the white dwarf. The white dwarf is the remnant core of the main sequence star. And of course, it's packed into a very tiny volume, basically the size of a terrestrial planet, but all this mass is packed into this tiny volume, so it's very, very dense. A lot of people know this, of course, but what a lot of people don't really realize is that white dwarfs also have atmospheres. So approximately 1% of the mass of the white dwarf is actually an atmosphere, which is usually composed of its exterior. It's usually composed of hydrogen, so it's hydrogen dominated in about 85% of the cases, and the rest are helium dominated atmospheres. So what happens is, if you have planetary debris, and we will talk about this, how these debris form and so on, but if you have planetary debris and they accrete on the white dwarf atmosphere, then you have all of these heavy elements in the atmosphere. And according to theoretical models, the heavier elements, the ones that are heavier than helium, they should sink very quickly inside the atmosphere on a time scale of maybe even days or weeks for hydrogen-dominated atmospheres, and maybe up to 1 million years for helium-dominated atmospheres. But it really depends on the temperature of this atmosphere. So it depends on the cooling age of the white dwarf, which is another word for the age of the white dwarf. So what we see actually when we look at these atmospheres, we see regular absorption lines. We see these features, and we see the absorption lines from heavier elements, heavier than helium. And what's really unique about that is, I just said that theoretically the sinking time is very fast. So you're not supposed to see all these elements there. The probability to do so is very low, unless you have ongoing accretion mediated by a disk. So as long as the disk lives and there is accretion, you get a replenishment of all of these high mass elements, and you see them in the spectra of the star.
I would expect that the time it takes to sink depends on the ratio of densities, no? Not just the temperature.
Yes, of course, it depends. So anything that is more dense, of course, than helium will sink fast. It also it's temperature dependent, but that is more important for helium-dominated atmosphere. So right. It's both dependent on the mass, but also on the temperature of the atmosphere. These models are quite complicated.
Well, but you know, how do you know what is the density of these other elements, like the iron or the magnesium or the other elements that you have there that you're seeing the lines?
What do you mean?
I guess you have a good modeling of the density gradient of the atmosphere of these white dwarfs. That's fine. But how do you know the elements that come? I guess they're in the form of some sort of a gas. So how do you know what's the density of this gas?
I don't think you can know exactly what's the density of this gas, but you can just think about them as individual atoms. Of course, the heavier atoms are going to sink in the atmosphere eventually, because if you calculate the equation of motion, you can show that the time scale for them to sink is quite rapid. You also have to remember that this is a high G environment, so that the gravitational acceleration of a white dwarf is like 1,000,000 times higher than what we're used to in a terrestrial planet, because it's proportional to the mass. So in this type of high gravitational acceleration environment, the sinking time is just quite fast.
What would be the density of the atmosphere now?
Again, it's not the density of the atmosphere, it's the density of the individual constituents, components inside the atmosphere. So if you have something heavier, sorry?
They would also be, you have to scale them as well with the gravitational potential that you have there.
Okay, I'm not sure that I understand your question then exactly. So,
well, I'm saying that you say that it's a high gravity environment, which I agree, of course. But then also the density of the atmosphere would be quite high, right? Much higher than in terrestrial planets.
Of course, but you're not more.
So this would slow down the sinking time.
Yes, of course it would slow down, but the important thing is the sinking time of only the heavier elements and not the entire, obviously, not the entire atmosphere, just the elements that are heavier than the counterparts, of course. So that's why I'm not sure that I understand exactly what you mean.
Okay.
Okay, can I continue? Or are there more questions?
I have a question. The elements, the heavier elements here in the atmosphere, are they ionized? Are they actually atoms? How hot is it in those conditions?
Well, the atmospheres of white dwarfs start at around 30,000 Kelvin, and then as they cool down, they start decline. The temperature starts to decline, but it's usually much hotter than typical stars like the sun. So it's even really old white dwarfs that are billions of years old. They're still like 9,000, 8,000 degrees Kelvin. So you should expect all of these, of course, all of these elements to be ionized, yes.
So these lines that you see are lines from higher ionization levels?
Yeah, for example, this is a famous calcium-2 line. So it's basically an ion of calcium.
Okay.
Like calcium ionized ones, of course. And so when people try to estimate how many white dwarfs are actually polluted with this material, between 1/4 to 1/2 of all the white dwarfs have these heavy elements in their atmospheres. So that's a huge fraction if you think about it. Around 1/3 of all of the white dwarfs have this polluting material. So it's important to keep that in mind for the rest of the talk. Yes, Asaf?
I have another question. How can you be certain that the material that you're seeing is pollution, right? This material is being synthesized inside the stars, right? During their main sequence phase, also during the red giant phase, right? So I would imagine that there is some turbulence there inside the star that puts some of this material in the atmosphere.
Okay, there are two other candidates. It's been established in the last decade that it's definitely not it. So it could be from the ISM, but it's been ruled out. There's just not enough polluting material if it comes from the ISM. And it could be, as you say, from dredge up, from material that comes because of convection and comes from the star. But this happens only in very young white dwarf. You mainly see carbon being dredged from the core. And this applies to white dwarfs that are hotter than about 25,000 Kelvin. As the white dwarf cools and gets below this temperature, people who work in this field, they estimate that this could not be the reason. So it has to come from the external pollution by this planetary cement.
Is there a simple way of saying why this cannot be the reason?
Again, it has to do with the dredge up, which it depends on the convection, and you need to you need to understand what sort of temperature leads to convection and so on. So, you know, I don't remember exactly what their underlying argument is, but I just know that this applies only to very, very young white dwarf and not white dwarfs that are older than, I think it's about a few tens of millions of years, basically.
Okay. How well can you measure the age of the white dwarfs?
I think it's basically established based on the temperature and theoretical models, of course.
Okay.
So, oh, there it is. So here's a nice story. In 2019, all of you know that the Nobel Prize was awarded to the people who discovered the first exoplanets. And so this carries a lot of importance because since the days of Aristarchus 2,300 years ago, this is the first proof that our planet is not the center of the universe. There are other stars elsewhere and they have other planets. And this is a proof that we are not unique in the universe and in our galaxy. But actually, what most people don't know is that the first proof of exoplanetary system is not from the 90s when they discovered the exoplanets. It's from 1917. In retrospect, we know that this is the first detection of an exoplanetary system. There's a famous star. It's called the Van Manen star. So this star was initially identified as just a faint star, an F-type star. An F-type star is a star that's a little bit more massive than the sun. And once you measure the distance to the star or the parallax, you can actually say that this star is faint because it's small, because it's a white dwarf, and not because it's very far. And this is actually when they later figured out that this star was a white dwarf, and it was a polluted white dwarf. And the protagonist of this story is Jay Farihi, is one of my colleagues. And he decided that he wants to get his hands on the original photographic plates from 1917. And it was a long process. He went to the Mount Wilson archives and he asked for this. And after a long time, he got his hands on this. And this is really an astronomical relic, an artifact, archaeological find of really the first detection of an exoplanetary system. And you can see very clearly the calcium absorption lines here in the spectra. So this is, in fact, in retrospect, the first discovery of an exoplanetary system. Later on, in the 2000s, 2007 was the first high resolution spectra obtained for a white dwarf. And what you can see here is they attempt to establish the relative abundances between various elements that you can see in the spectra. And then from this, you can infer the composition or the chemical composition of the polluting material. You just compare it to known things like the Earth ball composition or meteorite composition or comet composition and things like that. And they came to the conclusion that the material that's polluting this white dwarf is very terrestrial-like. It's very Earth-like. And then they started finding more and more of these white dwarfs with Earth-like polluting material until several years later, they found the first atmosphere that has really a lot of oxygen in it. So what I mean by a lot, by excess oxygen, is just more oxygen than what you would expect to find if you only look at the metal oxides, rocks that have oxygen in their composition. So this oxygen, this excess oxygen can only come from one place, water. Water is H2O. There is a lot of O inside water. And of course, if you accrete water-bearing objects, then you get this excess of oxygen. And this is the current explanation.
So again, just to make sure that I understand. So
yeah.
Yeah, looking at the atmosphere of white dwarfs, they are looking at the different absorption lines, and they are seeing absorption which fits into oxygen, and then they deduce from that that there must be some planet which contains a lot of oxygen that was destroyed and is now part of the accretion disk that sinks into this atmosphere. Is that
That is precise. It could be maybe a planet, like you say, or maybe it could be multiple planets. Maybe there's an entire remaining system of planetesimals and they all have a lot of water in them. Okay, so we don't know exactly what was the polluter. We just know that the pollutants have a lot of oxygen. So you can infer from that that there is a lot of water in this planetary system. Yes, that is correct. What you said is exactly what I meant. So later on, this was the first object that contained water. Later on, they found two more of these that have a high fraction of water in them. And also they looked at large samples of objects and they found that typically in a lot of these objects, they found dry material, terrestrial-like material. But in very rare cases, I'd say about 10% of the cases or even 5% of the cases, they do find polluting material which is rich in water. So the question now is why? And you remember from the beginning of the talk, I explained to you that the sun becomes a giant. So you can think about it. Of course, when something becomes large, then the luminosity is proportional to the surface area. So something becomes large, it becomes very bright, very luminous. And you can expect that the effect of that would be that icy objects would simply lose their water, maybe some of their water, maybe a part of the water because of insolation from the sun, for the star. And in order to say if water can actually be retained or not, the answer is that it really depends on a large number of parameters. For example, first of all, it depends on the star, of course. More massive stars are more luminous. On the other hand, they have a shorter lifespan. For example, our star lives for about 12 billion years before it becomes a white dwarf. But a 2 solar mass star lives for 1 billion years, and a 6 solar mass star lives for a few tens of millions of years. So more luminosity, but a shorter lifespan. Of course, it also depends on the minor planet. If you put the minor planets very far from the star, then less water is sublimated, or if you put it close to the star. Of course, it depends on the size of the minor planets, if it's large or if it's small. It depends on the sort of structure that the minor planet has. So it could be like a comet, the ice and the rock are all mixed together, but it could also be something like this, where you have a differentiated structure, a rocky core underlying an icy crust, then it's easier to get rid of the water. And also it depends, of course, on the composition, because some minor planets are initially, intrinsically, they have less water to begin with or more water to begin with. So it depends on all of these different parameters. And there's a really large parameter space that you need to explore in order to answer this question. Can water actually be retained during the main sequence phase, and especially the post-main sequence phase of the host star before it becomes a white dwarf? Yes,
and again, I want to challenge this entire picture. Again,
yes.
We know that oxygen is extremely abundant, and is abundantly produced inside the stars. So can it be that during the red giant phase, then the oxygen is ejected away of the red giant in the form of a wind, which never formed, which never has the opportunity to form planetesimals or planets. And this wind is gases oxygen and gases other elements that are being ejected. This is what forms this accretion disk that later on serves as what you call the pollution.
That's a very interesting idea that I've actually never heard before. It's the first time that I hear this question. Very interesting. But I would have to say, if I have a few seconds to think about it, of course, this stuff is blown away to really great distances, right? The planetary nebula is huge rather than, you know, a tiny solar system. So
you have plenty of time afterwards to sync back, right?
well, from a distance of light years to sync back to the star, it doesn't sound like something likely. And even if you do think that an accretion disk like this could form with a lot of oxygen and a lot of water in it, you'd have to account for where the hydrogen, of course, comes from. But even if you think that something like this could form after the white dwarf forms, once it accretes onto the white form, once it accretes onto the white dwarf, that's it, where you get more stuff, more water-bearing stuff. So,
I mean, you're assuming that your picture is that you start with some planetesimals,
yeah,
or planets, that then form a disk. And this disk, the material from the disk is slowly sinking into the atmosphere of this white dwarf. Now, so, you know, the first question I ask, how can you be so sure that this is not something which is internal, right? Something that actually comes from the star, because we know that all these elements are produced inside the star. And you said that this is something model dependent, and after long enough time, you don't expect that this material to flow into the atmosphere.
yes.
Fine. But now I ask you, during the red giant phase of the star, we know that red giants emit winds, right? We have different types of stars, and they do emit all winds. And we know, I don't know, I'm not an expert about red giants, but I know that you know, you have this convection inside the red giants, and we know already that this material, these elements are in there. So can it be that this material is just emitted as part of the wind, you know, the natural wind that is emitted in the red giant, and then eventually you said you have plenty of time until the newly formed white dwarf cools down, and this material sinks back, part of it, I guess, without the need to produce first the planets or planetesimals.
So again, when you say sinks back, are you talking about stuff from the planetary nebula that actually finds its way back to the star somehow?
Yeah.
What would perturb this disk or halo into coming back to the star?
You can have many things. I mean, you know, well, you had a slide with a long list of possibilities to produce planetesimals that would have high enough eccentricity to be so close to form the disk. I mean, but you know that you have like orbiting planets around that they can perturb the gravitational potential nearby. I mean, okay, I don't know. I have to think of that.
Right, but this is a
possibility was ever considered.
This is what you're talking about is a diffuse, low density halo of essentially gas, very low density material. So first, I mean, you wouldn't be able to perturb this material, would have to first form or coagulate this stuff into the planetesimals and then perturb these planetesimals. But I'm not sure that planetesimals would, you know, be formed in this kind of environment to begin with, because this is a very diffuse disk. It's not something that would have enough, you know, mass or density in order to form planetesimals. So I think a much more natural explanation is that, you know, stuff simply survives in the planetary system, survives the post-main sequence evolution of the star, and then is being perturbed. Like normal planetesimals, they just orbited the star before it became a white dwarf, and they still orbit the star after it became a white dwarf. I don't know why, you know, you should produce these planetesimals light years away and then perturb them inside the white dwarf. You know, it doesn't sound something that would happen.
But let me ask you something else.
Yeah.
If you look at the element abundances of the outer planets in the solar system, you know, the ones that would definitely survive the phase where our sun will become a red giant.
Okay.
What is the abundances of elements like oxygen and you know?
So this is exactly what I am coming to. So this is what I'm about to show. actually, there was no work that really did this at a high level with a lot of details. What is actually the composition of all of these objects that you're talking about, these objects in the outer solar system that survives to the white dwarf? How much water do they carry? This is what I mean by water retention. How much water do they carry after water presumably sublimates because of the post-main sequence of the star? So this is exactly what I want to show you next. This will answer your question. So I will continue. So remember, all of these parameters determine how much water will survive in these minor planets. And I happen to have developed a code. This is actually what brought me to the white dwarf field. I developed a code during my PhD that calculates the thermophysical evolution of minor planets. I developed it with Dina Priyanik from Tel Aviv University. And what this code does, I will not go into all of this complicated detail. I will just say it very shortly because I want to say a lot of other things in this talk. So first of all, it calculates the thermal evolution of the minor planet. So basically the temperature, the internal temperature, and also the heat flow inside of this minor planet. Also the physical evolution. So by physical evolution, I mean, if you initially have ice, then ice can sublimate, become gas, it can melt and become liquid. And then you have what we call multi-phase flow inside a porous sponge-like, what we assume is a porous structure inside this minor planet. So we have physical migration of the water inside of this planet as well, and also ablation or sublimation of water from the exterior. We also have chemical evolution, because once you have liquid water and rock, if the rock is initially anhydrous, if it doesn't have hydrogen on the molecular level, then it can become hydrated. This is a very famous exothermic chemical reactions, which means that it releases energy. It's a very important energy source for the thermophysical evolution of minor planets. We were actually the first to introduce these geochemical reactions in a self-consistent model. And also the mechanical processes, because remember the flow is initiated inside a pore space, but once something becomes hotter, so it becomes more susceptible to compaction as a result of the increase in temperature and the pressure by self-gravity. And all of these different processes, in addition to an orbital evolution of the minor planet, because you remember that the minor planet orbit actually expands as the star loses mass. So all of these really complicated physical processes are integrated into a very complex set of equations. And of course, you cannot solve these equations analytically, but you can solve them using a computer. So what I would like to show you is one example of such evolution that will illustrate what we did. We didn't do this by one or two examples. We did this by the thousands. We took thousands of different simulations of different objects, and we basically started them off with some amount of water and saw how much water we have in the end of the evolution. So what you see here is an object that has a radius of 600 kilometers. That's a good analog to Ceres. Ceres is the largest asteroid in the asteroid belt. So it's really a dwarf planet. And it's surrounding, in this case, a solar mass, one solar mass star, like a sun-like star. What you will see here is as follows. The color map is white for ice material. As ice becomes liquid, as it melts, it becomes blue. Rock is brown, unless it's hydrated, in which case it becomes olive. Molten rock is red, and the pore space, all of these black pixels are basically pores inside the object. So now what you will see is that this object forms during the first few million years of its life because of radiogenic heating. It becomes differentiated. You see this, all of this ice basically migrates to the surface, forming an icy mantle. The rock inside the core becomes hydrated, and then the internal core, the inner core, is even hotter, so it becomes dehydrated. It exudes all the water that it had previously absorbed. There is some melting in the core for a brief moment. And then during the RGB phase, the star becomes luminous, and all of this water sublimates to space. And during the AGB, the exterior rock is even baked, like you see here. So I will show this again. Differentiation, hydration of the core, dehydration and compaction of the inner core, some rock melting. You see all the pore space is gone by this stage. The core is very hot. And when we reach the RGB phase, the red giant phase, basically the stars become very luminous, and all of this water sublimates to space. You see here an evolution of 11.5 billion years. And what we did here in a series of papers that were, I think, first of their kind, and still are, we calculated thousands of different simulations of objects like this, of different sizes, surrounding a star like sun. And the next paper, we also investigated not only a sun-like star, but also stars of different masses. So we used the stellar evolution code called MESA in order to calculate the evolution of other more massive host stars. And in the third work, we also investigated not only small minor planets, but also dwarf planets.
What is exactly the role of the external star?
The role of what?
Is just the heating rate is changing?
Yeah, so you want two inputs to our model. The first input, you want the luminosity of the star, which you can obtain from MESA. And you also want the mass of the star, because as the star loses mass, obviously the orbit of the planetesimal changes. So these two things are important as input to our model.
No, how is the orbit entering your model exactly?
How does it end? It depends on the
enter, not how does it enter into the model? Is
orbit?
It just the orbit? Yeah. Is it just that the luminosity changes with time, or is there something else there?
Exactly. It changes the boundary condition, because the luminosity of the star, of course, the luminosity is the same, but as you go further from the star, so the flux reduces by the distance square. So you need the mass of the star and the mass loss in order to calculate what is the same major axis, what is the orbit, how the orbit changes. And that affects your boundary condition.
Okay.
Okay. So the end result of this study, we published a freely accessible program that anyone can download, anyone in the community. And it basically tells you how much water is retained in the end of the evolution. You take a planetesimal, you take a host star, you plot in the mass that you want, the size that you want, and all of these different parameters. And it tells you how much water is retained in the end of the evolution, and even how much ice is retained in the end of the evolution. So this was, I think, a nice step in understanding the sort of understanding why water is actually less abundant, because we show that water can survive in these minor planets, but it can only survive in minor planets that are pretty far away. And so it's another step towards deciphering this riddle, why you see mostly dry material, when we have long discussions about this in the paper. So just before I go to the second part of the talk, I would just like to mention that in recent years, we have the Gaia Space Telescopes, which determines the parallax, the distance to other stars, and maps the near neighborhood of our galaxy. And with Gaia, there is really an explosion in the number of known white dwarfs. Before Gaia, there were approximately 33,000 white dwarfs known, and now the number is almost tenfold. It's 260,000. So this is leading to a lot of follow-up observations and an enormous amount of exciting discoveries in recent years. All of a sudden, we discover more white dwarfs and so on. So the next part of the talk, I discussed the white dwarfs and the atmospheres and the polluting material. Now I will discuss the environment of the white dwarf, because we got a lot of questions about disks and so on.
Wait, Uri, before you go on, the
Yes.
calculator and the model that you presented, just as kind of a sanity test, what does it predict for the water on Earth? It's retained, it's not retained, it will evaporate away, it will be blown by the red giant phase.
First of all, the Earth itself is not even a question, because the Earth would be swallowed by the red giant star. So the Earth will not survive at all. It will be swallowed by the star. But if you want to look at something, let's say, around maybe the asteroid belt, so just look at this. Okay, this is the fate, the real fate of Ceres. This is what will happen to Ceres. It would basically lose all of its water. There will be no water left, no ice left at least, and almost no water left, because at the end of this evolution, all you have is a very thin layer of serpentinized rock, of hydrated rock. So this rock has some water on the molecular level, but only a very small fraction of water, okay? So if Ceres accretes onto a white dwarf, you might expect some access in oxygen, but only a very little bit on top of what you would expect from metal oxides. So the fate of the inner solar system, I expect all of the dwarf planets to lose all of their water. Yes, of course. Maybe you can survive if you're, I don't know, at the orbit of Neptune or trans-Neptunian objects and things like that. But in the inner solar system, unless you, I mean, even if you're a really large minor planet, you will lose all your water. Yes, definitely. And definitely at the distance of the Earth from the sun. Yes, of course. So part 2 of the talk, I want to talk about the environment of the white dwarf. So again, I will go through some of the milestones in this field. The first sort of paper that discusses the environment of white dwarfs comes in 1987. This is the first discovery of infrared access. So what you would expect to find is just the normal black body spectra of the white dwarf, but you see some excess in the infrared. And initially, I mean, the authors of this paper thought that this was a brown dwarf, which is a failed star, and it had to be very, very close to the white dwarf in order to produce this signal. But in retrospect, we know that this wasn't a brown dwarf. Later spectroscopic observations of this object revealed that this material has to be a dusty material. You can also see that this could be fitted by an extended disk of material, and also you can see some emission features from dust. This is similar features that you often see in ISM dust or in the halo of comets, for example. So you know that this stuff is not from a brown dwarf, it's actually from a disk. And it was later established that this sort of spectra you can fit with 2 components. The first component is what people consider the canonical model for the accretion disk of white dwarfs. So it's an optically thick and geometrically thin disk. You can imagine something like the rings around Saturn. And actually, the scale here is very similar. I told you that you expect something to disrupt inside the Roche limit of the star. If you do the calculation, the Roche limit of the star is approximately at a distance of 1 solar radii. And actually, all of the disks that we see, we can fit with this optically thick and geometrically thin disk inside the region which corresponds to 1 solar radii, so which is exactly the tidal Roche of a white dwarf. So the interpretation is that something comes in, disrupts, and eventually forms an accretion disk within this distance, the distance in which the tidal forces are more important. And nowadays, the count is approximately 50 disks that have this infrared access. And again, you can try and fit this empirically with an optically thick, geometrically thin disk. And also there is another component. There has to be an extended halo of some kind. Nobody really knows what it is. That has a optically thin dust, and from this you see the emission features, and they correspond to silicate dust features according to the models. So as you see, in the years that came after this discovery, more and more and more and more of these disks were starting to be observed. And today, as I said, we have more than 50. Some of them are actually very, very recent. And now that's not all of the story. There is infrared variability. So not only do you see this infrared, but it's not quiescent, it's not static, it's dynamic. Something is changing on the time scale of weeks and months. These two papers were the first to find this variability, and it was done from ground telescopes. In ground telescopes, you have a bit of a problem because you only have certain atmospheric window. You cannot observe all of the infrared. In order to observe the entire infrared, you have to send your telescope to space. And indeed, these very, very recent papers in just the last couple of years, they did a targeted survey on these white dwarfs that have this infrared access, and they found that they all have infrared variability. If you observe the white dwarfs twice, 3 times, 4 times, and so on, you observe them several times, you see that the infrared is variable, it's changing. It could be 10%, 20%, in some cases even 50%. These white dwarfs that have more variability also have gas in them, which is a clue, and I will talk about gas in a minute. So this is the next sort of milestone. Not only do you see the infrared variability and the infrared, you see also gas in these white dwarfs. The first sort of paper that found gas is in 2006. And you can clearly see the emission from a gas disk that's orbiting the white dwarf. By now, there are about 7 known disks, but in the last few weeks, only in the last few weeks, there have been several papers published based on what I just told you, Gaia, and a lot of follow-up observations of new white dwarfs, and the number of gas disks has tripled. What I should mention about this gas disk is that with the exception of one system, all of these systems that have gas, they're not exactly gas disks, they're gas components. So all of these systems belong to systems that also have infrared variability and infrared access, okay? So about 1/3 of the known infrared access systems also have a gaseous component. Now, remember that, yes?
Maybe I missed that. How are you sure about this is a disk? I mean, you're seeing a column density with excess of gas, that I agree. But how do you know it's in the form of a disk there?
So here you see that it's a disk by the double peaked morphology. So you basically, yeah, you know, so I don't have to explain. Okay.
Okay.
Okay. So all of what I've just explained is basically empirically motivated. But what about the physical motivation? What is causing this? What is the nature of this weird thing? I mean, you only observe, first of all, you see 1/3 of the white dwarfs are polluted, but only a fraction of them actually have this infrared access. Among those, some of them have gas, but some of them don't. You have the infrared, which has 2 components, and you have infrared variability. What is causing all of this? What is the physical motivation? What is the physical interpretation of this? Actually, until now, there has been no interpretation. But also, you remember that the canonical disk is a compact disk, is a circular disk, a ring-like disk. Why should you form this sort of a disk? I mean, you start from a tidal disruption, but you are disrupting something which is very eccentric. It comes from a distance of several astronomical units. So you expect it to form an eccentric disk. So presumably you form some kind of an eccentric disk, and then the disk evolves and shrinks into like this compact state, or perhaps it has more components to it. And eventually you have accretion. But the details of this are really, really fuzzy, okay? So we have some kind of tidal disruption, a planetesimal rips apart. This is just an artist illustration. It actually doesn't look like this. And you need to get to something that looks like this. But actually, as I will show in a minute, you see something like this. This is what you form initially. You form a very eccentric disk, okay? So what I would like to start talking about is a series of 2 papers that we published this year. And it's actually the first ever hydrodynamical simulation of a planetary tidal disruption around a compact star. This has never been done before. There are dozens of papers about TDEs, about the tidal disruptions of stars around supermassive black holes, but no one has ever carried out numerical simulations, almost with the exception of one work, which is very, very limited. No one has actually studied the disruption of planets or dwarf planets or asteroids, large asteroids around the white dwarfs. So this is the first. So what you see here, you see as I explained, the planetesimal. It comes within the white dwarfs and it disrupts. This is approximately the Roche limit of the white dwarf. So what happens is it depends on how deep inside the Roche limit you actually get. If you go very deep, very close to the star, you can see that you have a very violent disruption. You can see the zoom in here in this image below, and a large velocity dispersion among the particles. If you go very far, if you just skim the Roche limit, basically your planet or your planetesimal stays intact, and only very little material is being ripped apart from the planet into tidal streams. One of them is unbound in this case. I mean, it's unbound to the star, and one is bound to the star. It will come back to the star. And in the intermediate case, this is the sort of fiducial canonical model of what a tidal disruption looks like. You form a narrow tidal stream, which you can see in this image after it gets a little bit further out from the Roche limit. You can see that this tidal stream is gravitationally self-confined, so it collapses on itself to form these fragments. Some of these fragments, as I mentioned, are unbound. It means that they will go to interstellar space. And actually, in recent years, the first interstellar visitors have been observed. And actually, a lot of people think that they could emanate from exactly this sort of disruption, something that disrupts near a white dwarf and throws out material to the interstellar space. And all of these bound fragments, they each have now new orbits, new semi-major axes. They will eventually they complete their orbit and come back to the tidal Roche of the white dwarf, and they will disrupt again. Each of them will form its own tidal stream, and so on and so forth in an iterative process. Now, the reason why people don't numerically model this is because it's very hard, even impossible. Also, in the case of TDEs, what people do in order to numerically model this, they do 2 things. Either they take a very low resolution, and also they take a contrived orbit. They don't really take a very, very eccentric orbit, because if they take an eccentric orbit, they will have to model all of these fragments for a very long time, and this is computationally impossible. And so what we did here is we employed a new hybrid technique. To the best of my knowledge, this is the first time that it's been done. So what we do is we say, okay, for the hydrodynamical code, we only care about what happens inside the vicinity of the star. We want to really follow in detail how the tidal disruption occurs. But later on, we can take each one of these fragments and we can just immediately and magically transport them back to the Roche limit of the star. We can assume a Keplerian orbit, and so we can treat this analytically. So the hybrid model is a SPH hydrodynamical plus analytical model. What we do here is all of these calculations of tracking the fragments when they're far away from the star become redundant. You don't care about this. You only care that the hydrocode actually calculates the actual tidal disruption of these fragments. So everything is tracked and synchronized. We make sure that as these fragments come back to the star, we get the timing right. And so we build a disk from these calculations that otherwise you would not be able to do with a full hydrodynamical simulation. And just to illustrate what I'm talking about, okay, this is what a full hydrodynamical simulation would look like. A planet, in this case, Earth-like planet, goes near the white dwarf and tidally disrupts, and you see how the, maybe I will repeat this. You see how the fragments form. Each one of them forms its own tidal stream, and so on and so forth. And this simulation here is a full simulation. What I did here is I took very low resolution and I put the planet very close at a distance of 1/10 of an astronomical unit, because otherwise I would not be able to calculate this. And it still took 4 months to do this simulation. On the other hand, the hybrid simulation did the same thing in 2 days. And of course, if you take a very eccentric orbit from several AU or several tens or several hundreds of AU, the difference would be 10 orders of magnitude in runtime. Okay, this would be impossible to do with any computer, even the largest supercomputer in the world. And this is easily done. And not only you can do this for any orbit, you can do this for very high resolution. So we went from several thousand of particles, which is very few in nowadays in hydrodynamical simulations. We went to 500,000 particles. And we take any orbit that we want. So this is really a first time, and the result between this model and this model are exactly identical. So there's no difference between this model whatsoever.
Again, so the trick is to simply use Keplerian orbits once you get far enough from the star.
Yes.
Okay.
Okay.
How many particles do you have in your SPH?
So 500,000. I said. Yeah, that's the largest resolution. I can do more, but it will take. I think 500,000 took me 2 weeks.
Okay.
Do you only do the?
Yes, Ofek?
Sorry, had a wrong mute button. So do you only follow the Keplerian orbits to save this computation time, or can you include sort of corrections from the bulk of the other mass in the disk, or can any other sort of multipoles, any other effect that's a correction to just a bare Keplerian?
It's an analytical model, so you can input any sort of correction that you want. It could be from radiation, for example, maybe the Yarkovsky effect or some Opera drag, or some kind of effect that you want. You can enter any sort of analytical correction that you want, but we just do the Keplerian orbit, yes. So you start with an eccentric disk like this, not like this, but you want to get to something like this. Okay, that's the first problem. Also, you want to explain the gas production, as I said. You also want to explain why gas is only seen in a fraction of cases. You want to explain what is exactly this infrared excess, where is it coming from, and where is the variability coming from. All of this is just a really big riddle. We don't know how to explain this. So as recent as last week, this paper was accepted to M. and Russ. I wrote this paper with 2 PhD students, one from the Technion and one from Cambridge. And we have a model that I think is okay in actually being the first model that self-consistently can explain all of these things together. So what we envision here is as follows. We think that this is the canonical compact disk that's typically made up of dust. And so we think we start our model at the end of this evolution. So in the end of this evolution, we have an eccentric disk full of fragments. These fragments are in the size range between 10 meters to 1,000 meters, according to various theoretical works. So these fragments come to the disk, they collide with the disk, and they dissipate orbital energy. So you expect them to circularize on some time scale. Of course, this depends also on the size of the planetesimals or the fragments. And you can see here, of course, I'm leaving out all the boring mathematical details, but you can see here that this circularization time depends on several parameters, of course, on the mass of this compact disk. So its mass, its density, and so on, and the distance of these fragments from the white dwarf. And also on the size, most importantly, on the size of these fragments. Okay, so the smaller fragments, they circularize faster before the larger fragments. And what happens is we show that this is an inescapable result of colliding with the disk. You form gas. So previous models that try to explain why there is gas in this disk, they couldn't do it, because if you have simultaneously gas and dust, the gas should very quickly condense on the dust grains and disappear. So in order to have ongoing gas, you have to have some sort of replenishment. You have to have something that forms the gas repeatedly. And in our model, it's not a problem, because you have this influx of fragments. It continues, and as long as it continues, you form the gas. And so initially, you have more of these fragments, and we show that you form this gas continuously. And as the tidal stream evolves, a lot of these smaller fragments become embedded in the compact disk. They become embedded and eroded in the compact disk. And so later on, the gas production becomes intermittent. So you do have gas production, but you don't always see it. It's a question of probability. So this explains why you see gas only in a fraction of these cases where you have a compact disk. So we also, yes.
What is the process of gas production here? It's just erosion of material?
Yes, I will explain. There are a number of mechanisms that can produce the gas. First of all, you can have sublimation of dust, but this mostly happens around this region, close to the star. Okay, so this couldn't explain gas somewhere else. We think it's caused by collisional vaporization. So if you have, consider that these objects, that these fragments are coming at a huge velocity, hundreds of kilometers per second. At these velocities, if something impacts with dust grains, the dust grains immediately evaporate, okay? In turn, the fragment itself is being eroded. It's basically being cratered by the dust in the compact disk. But we show that later this emanating ejecta also becomes vaporized by interacting with the dust in the disk. So by these two reasons, you actually produce a lot of gas. And as long as you have these collisions, you produce this gas all the time.
Different than the asteroid belt that we have?
So what was the question, sir?
How is that different than what we have in the asteroid belt?
In the asteroid belt, gas formation in the asteroid belt?
Yeah.
Nowadays, with the solar system, you mean?
Yeah.
Nowadays, I mean, basically the only way to form gas would be by catastrophic collisions between asteroids. But in the asteroid belt, that would actually not generate gas unless you have water in these asteroids. And you do have water. I mean, in the asteroid belts, this is from the last decade, we now know that some of the asteroids are actually comets in disguise. They have water, but only inside, okay? So they have an exterior layer that causes mantling effect, that the water is not sublimating unless it is exposed by collisions. So if you have collisions between asteroids in the asteroid belt and they have water, then of course you can have sublimation of the released ejecta, which is water rich, and you can have gas. But otherwise, I mean, this is nothing like what we're talking about here. These are very, very high velocity collisions. So it's completely different.
What is the size of this disk, just to get a feeling?
The Roche limit. So by fitting the infrared and by fitting the gas emissions and all of these things, you can determine that these disks are approximately within the Roche limit. So between 0.2 solar radii to approximately 1 solar radii, approximately. Which makes a lot of sense because this is where you would expect stuff to tidally disrupt, okay? So anything that's exterior to this would remain intact, but anything that is interior to this would tidally disrupt unless it has some internal strengths, okay? You and I are inside the Roche limit of the Earth, but we're okay, we're intact, we don't disintegrate. It's because we're not governed by in the gravitational domain, we're in the internal strength domain. So anything small enough with a monolithic, internally strong structure can survive inside here, but anything that in the gravity-dominated regime cannot. Okay, so in our model, we also have a gaseous halo and a dusty halo, in which stuff is scattered from these collisions and sometimes from interaction between the fragments and this gaseous halo. And you can have stuff, gas condensing in this outer external region, and then this gas evolves by a Poynting-Robertson drag, which is an effect caused by the essentially radiation effect, and it migrates inwards, and this would be compatible with also a time scale of days or weeks or months. It just depends on how far it is from this boundary. So we think that this, yes.
I just wanted to comment. We're about an hour, 10 minutes now into the talk, and it's okay to go over, but aim to finish in about 10, 15 minutes. We've also had lots of questions, I know.
Okay.
Kind of keep that in mind.
Okay, thank you for mentioning the time. There were a lot of questions, so this is taking longer than I thought, but yes, I think I'm nearing the end here. So I'll go briefly on this last part in which we talked about the white dwarfs themselves and their atmospheres. We talked about the environment and the disk of these white dwarfs. Now I'm just going to show you some really cool discoveries from recent years in which you directly or indirectly see minor or major planets orbiting these white dwarfs. So no longer a disk, but something more particulate, something more substantial. So the first discovery is from 2015, and this made a lot of headlines. It's actually the first transit that you see in a white dwarf. Every 4.5 hours, you see this light curve dip, this dip in the light curve, and it has an asymptotic morphology, which means that it's something like maybe not like a spherical object, but something that looks like a comet. It has a halo and a tail, at least this is how it is modeled. And the interpretation of this is that you have something that's orbiting just outside the Roche limit, and it's slowly disintegrating because of the tidal forces from the white dwarf, and it's emanating this field of ejecta, and this is what's causing this transit. So this is really an interesting, important discovery and the first transit seen around the white dwarf, but it's not really a planet, it's more like an asteroid. Last year, there was another important paper about the first white dwarf disk that actually has gas, but not infrared, but not dust. So it's a very unique disk. And again, the interpretation here, this disk has lines from gas, but also from oxygen and sulfur. So the authors of this paper think that this could be something like an icy giant, like Uranus or Neptune, that's very close to the white dwarf. We don't see it directly because there's no transit, but it's close enough that the atmosphere of this icy giant is evaporating, and it's emanating all of this material, and this could actually explain the composition of this gas that they're seeing. I actually communicated with Boris Gansicki because I have another idea. I think that it could also be a partial disruption of a Uranus-like giant planet. So here you see like preliminary results of these simulations of a icy giant going near a white dwarf. And the idea is that you have only a partial disruption, so it doesn't come close, it comes close to the Roche limit, but not exactly inside the Roche limit. And every time it leaves out a little bit of mass from the envelope. So we model this with a core of silicates, an icy mantle, and a gas envelope. The gas is composed of helium and hydrogen in solar abundances. And you basically, every time you come near the white dwarf, you release some of this material, and over several flybys, perhaps you'll be able to form a disk that looks like this disk. So this is just preliminary results, and I have to come back to this in the future. Another discovery here is a white dwarf that has a disk, and it has a gaseous component. And the authors tried to follow up on this white dwarf. They were expecting to see random variation and variability in the gas emission. Instead, what they found was periodic variability. So they concluded that what they see here is something that, as I explained, strong enough to survive inside the Roche limit of the star, maybe a dead core of a planet. So it's maybe made out of iron and nickel, and it survives inside the Roche limit, and it just perturbs the gas, or maybe it's emanating some of its own gas. So that's the current interpretation of the system. And almost last, recent discovery from this year, this is the first ever transit of a white dwarf by a planet. You can see this very clearly by various telescopes from the ground, from space, and you see almost half of the light from the white dwarf is blocked. This is because white dwarfs are very small. And this is a giant planet, okay, according to their model fits. So this is also a first. It made headlines a few months ago. And I will conclude by saying that there is also very recent work this year, initial results showing more transits. But these transits don't look anything like this transit. They're very sort of random. Maybe they're caused by different fragments from different orbits, different sizes. Maybe they're round fragments. Maybe it's more like halos. We don't really know. So there's an entirely new class of deeper stars, stars that have these weird transits. And there is no canonical explanation for this phenomena. And I think with our model that we can produce these disks, and maybe we can create some sort of model and show that different disk morphologies can create different types of transits, and maybe try to explain these cases as well. So with this, I will conclude, and I will take questions. Thank you very much.
I have a question.
Yes.
So you didn't answer. Eventually, what is the expected rate? I mean, in order for this model to work, you need to get planets or planetesimals to have a very high eccentric orbit that would reach into this stellar Roche lobe of the white dwarf. So, what is the expected rate of the various mechanisms? You didn't really describe what mechanisms would cause it, that would produce this very high, extremely high eccentric objects.
Well, it's an excellent question, and the reason, the honest answer is I don't know. We didn't go into this in the model. We just assumed that some objects are being injected into this orbit. And the reason it's hard to say is because you saw all of these papers that tell you how or how many objects will be injected into this orbit. And each one of them depends on a different configuration. So I guess it depends on what configuration you are assuming. Are you assuming a system with 2 surviving planets, 1 surviving planet? How many asteroid belts are you assuming? Are you assuming this is from escaped moons? Are you assuming this is from an exo-Ur cloud? It depends on what you are assuming. And I guess someone, a dynamicist, would have to go through all of these different cases. Maybe someone like Hagai Peretz, someone, will go through all of these different cases and maybe try to establish, okay, what is the probability to get these eccentric orbits overall, if you consider all the different configurations. But I think it's a very tough question to answer. It's really like almost impossible to say what will be the rate of injection and what sort of objects will be injected. We do say in our model that, of course, in order for the model to succeed, you need a pre-existing disk. Now recall that you only have this disk in a very small fraction of orbit, a small fraction of white dwarfs. And we think that it's because when you have a progenitor that's actually more massive than the disk, it transfers angular momentum to the disk, and the disk disperses. So it all depends on the ratio between the mass of the compact disk and the mass of the progenitor. So this implies that you could explain this maybe if you go into maybe a size distribution of the injected planetesimals or something like that. But it's also complicated. I can't give you a precise answer. You realize that there's so many different possibilities and options.
Okay, maybe you can reverse the question and ask, given the disks that we are seeing, well, the interpretation we have that these are disks, what should be the rate of, objects of, I don't know, Earth-size objects that would get into a, such a high eccentric orbit?
Right, and this is, of course, can be done, but for this, you have to assume that you believe the model. So it was published a week ago. Let's see if people believe it and people think it's good enough, and perhaps yes, you can inverse the logic and try to establish maybe from this what is the fraction of large planetesimals that are being thrown into these orbits. But actually, one way in order to form this compact disk is to have these more massive progenitors. But we discussed several other possibilities in which you can form this initial disk, and it's not necessarily just through massive objects or objects that have a lot of volatiles, because if they have a lot of volatiles, then you have shocks in the gases, and maybe you can produce this disk in the first place. But there are other effects like radiation effects, for example, the Yarkovsky effect that can circularize maybe an initially eccentric disk, and maybe Poynting-Robertson drag if you have dust. So maybe you can produce dust if you have a lot of cataclysmic collisions, and you produce dust, and then this dust can go on to circularize. So there are a lot of different possibilities. And I plan to follow up on this with Mark Rowers. We have at least one paper that we want to write about this possibility of collisions between asteroids and the subsequent circularization of the disk.
Okay,
thank you.
So we had one student question in the chat during the talk. Daniel, if you feel you have not been answered, you can ask now, or if any other student or if anyone wants to ask some student questions, now would be the time.
Yeah, hi, thank you. So just regarding one of the first slides where you showed, where you talked about what would be what would be the causes of the different influences on the disk afterwards, on the absorbed matter. And you said that planets, it depends on how the planet is, where's the water in the planet? Is it inside the rock, or is it two different layers? Like first it's the rock, the inner layer, and then water. So from what I know, water is believed to be on Earth due to comets that crashed here before there was an atmosphere here. So why would there be another type of formation of a planet of water within the rock all the way through to the core?
Okay, so actually, water is very ubiquitous in the solar system beyond what we call the snow line. And even as I explained, even in the asteroid belt, we know that the interior of asteroids actually have a lot of water. Ceres, for example, has a very low bulk density. So you know, even from the bulk density, that it has a high fraction of water inside. Otherwise, you could not explain this bulk density. And so in the outer solar system, not only comets have water, moons have water. All of the moons of the outer planets, they have water. In the Kuiper belt, the region beyond Neptune, all of these objects have water, and we can even constrain how much water they have. One of my earlier works is on what is the composition in the Kuiper belt, and we think that it is, I mean, we predicted that it is something like 3:1. The ratio between rock to water is 3:1. And this is actually very compatible with recent finds of comets that come from this region. For example, P67, the famous comet that has been monitored heavily with the latest mission, actually has a similar rock to ice mass ratio. So water is ubiquitous in the solar system. It's in moons, it's in dwarf planets, it's in comets, you name it, it's everywhere.
Okay, thank you.
I have a question.
Yes.
The model you explained that when the white dwarf is formed, the heavy elements sink in compared to the light elements in the atmosphere. So what is the typical time scales of these heavy molecules to sink in?
Okay, so for hydrogen-dominated atmospheres, it's between days to weeks. And for helium-dominated atmospheres, it's between maybe, I don't know, years to even 1,000,000 years, but it depends again on the cooling age of the white dwarf. And this is all model dependent, of course.
Okay, so it's a very slow process. Yeah. Okay.
Yeah, well, slow is relative, of course, yes.
Yeah.
Any other questions?
Yeah, I have also one question about the last simulation, that it is like they assume that it's a giant planet. It's like, I think it's from 2020 something. And how this giant planet survive, like it was in a system of the white dwarf, and then it's stay outside, or it's giant planet from another system, or in their paper how they assume that it survive and it perturbates and affect the white dwarf.
Okay, if I understand your question, are you referring to this study or this study?
Yes, this one.
This one. You're asking how come it can survive, and you're absolutely correct. It's not entirely understood how you can get this object to shrink its orbit. Okay, because it's, if I remember correctly, this transit occurs every day and a half. So it's very close to the white dwarf, and of course it couldn't have been there before, because if it was there during the main sequence, you're right that it would have been swallowed by the expanding star. So there are a number of works by Dimitri Veras, 1 or 2 papers, I think, and they assume that this happened because of tidal dissipation. So basically dynamical tides.
How does it work?
How does it work? Just basically the planet is being dynamically stretched every time it passes near the white dwarf during perihelion, and loses orbital energy. So eventually it shrinks. But I never read this paper in detail, so I don't know what sort of assumptions go into their model. So.
Okay, thank you. Thanks.
Okay.
Not sure that I understand this. So it's tidally, so okay, so it gets, I assume the eccentricity here is quite low.
Now it is, yes. Well, now they don't know what the eccentricity is, but they can, they assume that it is, between 0 and something that, yes, it's quite low, if I remember correctly.
So how can tidal tidal effects lead to a change of the orbit, shrink of the radius? You have those orbital, potential.
So again, I'm not sure that I don't want to give you like a contrived answer because I haven't read this paper, so I'm not really sure what goes into their model. So I would have to look into it actually, to be honest.
Okay, fair enough.
Yeah.
Okay, I'm going to make a slight interruption just to announce that it is noon. So I'm stopping the official recording. Anyone who wants to, of course,